Hi everyone, this tutorial is a continuous tutorial from previous tutorials about Stack. Today we'll be looking at some implementation using Python. Now, Python built-in data structure list can be used as a stack. So instead of push, we use append to add element to the top of the stack. Pop, we remove elements from the top of the stack, which is last in, first out. Append in English means extra item on top of the list. That's the meaning of append. So here we're not using pop function, we're using append. However, while we're not using push function, we're using append. While pop is pop. So stack in Python, a stack is implemented using a list object. So to push an item in the stack, as I mentioned, we use the list function append. Okay, so we don't call it list dot push and then the name of the item. We call it append. Like I said, append in English means adding extra thing or item on top of the list. So to pop an item in the stack, we use the function pop. Now, unfortunately, the list has a few shortcomings. The biggest issue is that it can run into speed issues as it grows. The items in the list are stored next to each other in the memory. So if the stack grows bigger than the block of memory that currently hold it, then Python needs to do some memory allocation for that. This can lead to some append calls taking much longer than other ones. So let's have a look at some examples in Python. So I have this simple code. So here I've declared the stack. So if I go here, so we have here, I've declared my stack. I left it open so I could add to it. And then you can see here I have stack dot append. So A, and then stack dot append B, stack dot append C. And then here I said print initial stack, print what I've declared in here. So if I execute, as you can see here, we say initial stack A, B, C. 3 element. Now if I go and then go stack dot append, then let's say we add D, A, B, C, D. Okay, execute. Here we have, as you can see, A, B, C, D. As you can see here, we defined, as if you, I mean, it's showing here, it says append object to the end of the list. Kind of it's here when we define it. So if I go and add another one, stack dot append, then let's say here, I want to add E, A, B, C, D, and E. I execute. As you can see now, my stack has grown from ABC to ABCDE. So now let's move on to the popping side of it. Here, I'm going to continue. So here I've said print here just information for the user. Element popped from the stack. Here, as you can see, print stack pop, print stack pop, print stack pop. So here I'm popping the last 3 in out. So I'm popping the what's last 3 in. So what that means, so remember when we had A, B, C, D, E. So what are the last 3? That would be E, D, C. So if I execute, so what is going to print for me, what's kept it's only the A and B because it's popped last in, first out. So if I delete that, and I'm going to go execute, then as you can see, gave me back A, B, and C, and those the last 2 here I added earlier got popped. And if I delete both here, then it's going to give me basically nothing. Okay, so I mean, gave them back, but I mean, sorry, if I say, let's say pop all 4, 1, 2, 3, 4, 5. Then as you can see, we got nothing here. Stack after element are popped, nothing. And if let's say we remove one here, execute, And then, as you can see, it gave me back just the A because that's the last one. Everything else got popped in the order of E, D, C, B, and A. But we kept it in this example. So, what about assembly push and pop? The stack has its own register called a stack pointer, SP. This tells us how many items are currently stored in the stack. This value starts at 0 and grows for each piece of data stored. So let's have a look at this example. Here, the first line, it just that we're using hashtag, we're just saying to ignore, to jump, to ignore that line. Do not execute it. That's just information for us. Okay, push and pop. In line 2, as you can see here, we set R0 to be a value. So R0 here to be a value. Then the value is 9. Then we push it to the stack. Yeah, we push it to the stack. We then modify R0. We modify R0, as you can see, R0 equal 9 plus 1. And then we pop the data from the stack. It's quite simple example. So the stack is loaded into the end of the program memory. And basically, if we run it now, I'll show you. If I go into Cocoa IDE, you can see here the code. We have it loaded. So here, compile, reset, and then start. As you can see here, we have the value. So before we push the stack, the pointer SP should be 0. Once we push the stack grows, and the SP should be 1, 0, 1, and then if it grows again, then goes 0, 2, and so on. Okay, here, as you can see here, we say R0 equal 9, SP minus equal 1, SP plus equal 1. What that means is basically means SP equal SP plus 1, because here we're incrementing. While here we say SP equal SP minus 1, here we are decrement. So this means SP equal SP minus 1, but we normally write it that way just to make it easier and faster for the developer to just write it. So it's the same. I mean, once you do Java, it's kind of, we sometimes use this abbreviation to get things faster. But what that means here, just to avoid confusion, SP equal SP plus 1. And here SP equal SP minus 1. So whatever in SP here, we add 1 to it, and here we minus from it.